All right, we are in section 5.3, talking about the definite integral. So everything we've done up until this point has been dealing with an indefinite integral that's creating a family of functions. We get that plus c, that constant of integration, tagging on to the end of the formulas. Now we're going to be looking at what happens when we evaluate integrals over a specific interval. So we're going to start off by introducing the fundamental theorem of calculus. So it took us all the way to chapter 5, but we made it to the fundamental theorem of calculus. This is often abbreviated the FTC. And it says, if f of x is a continuous function on an interval from a to b, with a being less than b, and capital F of x is an antiderivative of our function, then the definite integral of f of x from a to b is given here. So this is the integral from a to b of f of x dx equals big F of b minus big F of a. So we take the antiderivative of our function, and then we evaluate it at the upper endpoint here, and then evaluate it at the lower endpoint here, and then subtract. So find the difference between the two of them. And that's going to give us the value of the definite integral. This value, whatever it is going to represent the total amount accumulated by that antiderivative function as x increases from a to b. So when we talk about the interval and those values themselves, the number a is called the lower limit of integration, often just referred to as the lower bound. And the number b is the upper limit of integration, or often just referred to as the upper bound. There's an important difference and distinction between the indefinite integral that we've been using and the definite integral that we're going to try using going forward. The indefinite integral produces a function, okay, or really a family of functions, but the type of object it produces is a function. The definite integral produces a number. And this is a key difference between the two. The indefinite integral, you're going to have a formula in terms of x with that plus c on the end. The definite integral, you're still taking the antiderivative, but because you're substituting in specific numbers into the formula, you are going to get out a number as a final answer. So this is one kind of quick check to make sure that you answered a question properly. If you have an integral with bounds on it, so a definite integral like this, your final answer should be a number. In terms of properties of definite integrals, so some of these properties are the same as the ones we've seen for indefinites. Like the first one, if you have a constant multiple inside the integral, you can still pull it out. This number 4 down here, if you have the definite integral of f plus or minus g, that's the same thing as the integral of f plus or minus integral of g. So those two are the same as what we've seen before. For the second one back up here, if you take the integral from a to a of f of x, that means on the graph, like you're taking, here's the function f. You're going to evaluate the integral from here to itself. And so we didn't accumulate any value in here, so we're getting a number 0, okay, for our output. And you can still show that algebraically, because you would take f of 0 minus f of 0, and then you would just get 0. The integral from a to b is the opposite of the integral from b to a. So if we switch the bounds, then we end up flipping the answer, okay? Flipping its positivity or negativity. And then the last one down here, if you take the integral from a to b of a function, you can actually split that into multiple integrals that split the interval. So if we had a function f like this, and this is a, and this is b, the integral from a to b is the same as the integral from a to c plus the integral from c to b. So instead of taking the whole thing at once, we're taking the two parts separately. And we are allowed to do that. That's what this property tells us. So let's take a look at an example. We're going to evaluate this definite integral. The evaluation of an antiderivative does not change. So we're still taking the antiderivative the exact same way, but now we just have a little bit further to go. So let's take the antiderivative. So that's going to be 1/3 x cubed plus 3/2 x squared minus 2x. Now, the nice thing about the definite integral is you know that we're going to be evaluating between two values, in this case 3 and 5. We don't need to include the plus c here. We're just going to put this evaluation bar and evaluate from 3 to 5. So let me make a note of this here. So we don't need a plus c. The reason we don't need the plus c is because as soon as you take, this function evaluated at 5 and you subtract the function evaluated at 3, this one would have a plus c, this one would have a plus c, and you would get c minus c, and then those would be gone. And it would do that every single time. So we don't have to put in a plus c anymore. If you forgot and you included one, it would just end up disappearing anyways. This bar that I drew here, so this is an evaluation bar. This is how we indicate that this function is being evaluated from 3 to 5 without using the integral symbol anymore. Because remember, the integral symbol indicates that we're taking an antiderivative. So once we've taken the antiderivative, we still want the 3 and 5 to show up here so that we know to use them, but we don't want to put the integral again because we've already taken the antiderivative. So from here, this now becomes a matter of substituting in the values. So we have f of b. So remember, it's the top value minus the function evaluated for the lower bound. So we get, let's see, 125 over 3 plus 75 over 2 minus 10. This negative will distribute to every value of the function. So we get minus 9 minus 27 over 2. And then this would have been negative 6, but it becomes plus 6. There's a little bit of work to do here with combining the fractions and getting the common denominator, simplifying, all that good stuff. But if we go through that algebra, we will end up with 158 over 3 So notice we got a numerical value. Okay, so we took the antiderivative just like we're used to, and then we evaluated between the upper bound and the lower bound, subtracted, and got out the number. We can also evaluate definite integrals using substitution, like we saw in the previous section. But in the previous section, we didn't have to worry about bounds. All we had was the antiderivative. So we're going to see there are two different ways to approach substitutions when a definite integral is involved. I'm going to show you both. So for the first one, our first solution, we're going to solve the corresponding indefinite integral. So the first way that we can approach this is by basically just ignoring the fact that it's a definite integral, go through our process of taking the antiderivative and then bringing the bounds back in after. So we would take the indefinite integral of 1 over x minus 3 dx. We can get our u as x minus 3. And this one's a pretty simple substitution because we didn't want to overdo it when we're trying to learn something else that's new. So we get, let's see, 1 over u du. So the antiderivative of this would be ln of the absolute value of u. And then we switch back to x. So ln absolute value of x minus 3. So we got the antiderivative formula here. So that's going to allow us to then set up the formula we just got, evaluated from 4 to 10. So we get ln of 10 minus 3 minus ln of 4 minus 3. So that's ln of 7 minus ln of 1. ln of 1 is 0, so we can go ahead and just put ln of 7. And that would be our solution. Now, I did mention there are two ways of approaching this type of problem. So the first is to solve the corresponding indefinite integral and then use that with the bounds. The second way is to convert the bounds using the substitution. So with this method, we're already converting all of the x's into u's. So the idea is we could take these x values of 4 and 10 and convert them into u values, and then just solve the whole integral in terms of u. So if we set this up, so integral from 4 to 10 of 1 over x minus 3 dx. So the substitution is the same. There's nothing new there. So we get integral of 1 over u du. But this time, we're going to also convert the 4 and the 10 into u values. So when x equals 4, u equals 4 minus 3, which is 1. Right, so just using the substitution. So instead of x equals 4, we get u equals 1 right here. And then when x equals 10, u equals 10 minus 3, which is 7. Now we take our antiderivative, ln of the absolute value of u, but now because we converted the bounds, we don't have to switch back to x anymore. We can just go straight into the evaluation from 1 to 7. So we get ln absolute value of 7 minus ln absolute value of 1. Again, don't need the absolute value. These are positive numbers now. Ln of 1 is 0, so we're left with ln of 7, which is, of course, the exact same thing that we got back above. Whichever method you like to use better is totally up to your personal preference. General kind of pros, cons for these. People generally like the first one because you don't have to worry about the bounds until the end. So people kind of like having that mental separation of just taking the antiderivative first with the substitution and then afterwards coming back and doing all the bound work. The downside of that one is it does take a little bit longer, and sometimes people forget that there were bounds on the original problem. So a lot of people that solve it like this would probably just try to box that as their final answer and just forget that there were bounds to begin with. For solution 2, the pros for this one, again, by not having to switch back anymore, it does shorten the solution a little bit. It makes it a little more streamlined. And the ability to not switch back is pretty nice. And on the flip side, the cons that people typically trip up on is converting the bounds properly, because you have to set this one up correctly in order to be able to follow through with it. But again, both of these are perfectly valid methods of solution for integration by substitution, and it would be up to your personal preference to determine which one works best for you. But that is just our brief introduction into definite integrals. When we come back in section 4, we're going to be looking a little bit more at the definite integral and kind of what it means visually and geometrically. Do a couple more examples, and then that'll get us out of this chapter. So I will talk with you all in the next one.